usually like to do, we can start with announcements. We have an exam a week from tomorrow. So you can expect a study guide to be released by tomorrow. And we will have a review period a week from today, where I will answer as many questions as people can come up with. And any topics that require extra practice problems. I expect that people will want some pumping lemma practice. I expect people will want some additional practice on some other topics. There are quite a few other topics. Let's see. I didn't get out the new assignment, did I? I need to do that. So yeah, you can expect a new assignment today that will be due next week as well, getting you practice on everything since the pumping lemma. We haven't really covered much since the pumping lemma. I don't know how much sense that makes. I don't know. I'll make an executive decision on that when I get back to my office. We're going to be covering a good chunk of that content today, though, or at least starting it. So yes, today we're going to start talking about PDA. And no, I don't mean public displays of automata. I mean push down automata. Although I guess technically this class kind of is public displays of automata. It's a weird way to think of it. So what are we doing? We are looking at the class of languages that are considered to be context-free languages. These are all languages that can be represented by context-free grammars. And we talked about different ways that we could represent context-free grammars and manipulate them to be useful to certain algorithms. We talked about Chomsky normal form, Greibach normal form. But what else can we do with this language class? It turns out that there is a form of automata or a state machine that can represent this type of language. And it's a bit more complicated than the DFAs and regular and NFAs that we've been producing for regular languages. So let's see if we can generate again that difference between a regular language and a context-free language, because I think that will help to motivate why we make push-down automata the way that we do. So what's the difference between a regular language and a context-free language? Entire class?
The regular language has to be either right linear or left linear, if I'm not mistaken.
Yeah, for the grammar.
Yeah, the grammar, and then the context-free, I think it just has to have either one non-terminal or a series of, or one terminal or a series of non-terminals, I believe.
That'd be like Greibach normal form. But yeah, in general, you can have any number of terminals and non-terminals on the right-hand side, and it represents a context-free language. We just wanted to then find a couple of useful forms for this because you can put them into a bunch of different forms. But yeah, from the grammar perspective, that is absolutely the difference between them. At an intuitive level, kind of abstracting from how we've been talking about grammars or state machines, what was the form kind of a regular language, and how does that differ from the form of a context-free language?
I mean, the big difference is you always have to have the non-terminal on either the left or right side, I guess, in the grammar, but.
Yeah, there was a big restriction just about representing these languages in terms of, we knew that a DFA had to have a finite number of states and grammar had to have a finite number of productions, each of which was right linear or left linear, which meant in the big picture that a regular language had to be representable with a finite amount of memory. Even a language with an infinite number of strings, we had to be able to accept or reject those strings with a finite amount of memory. So a context-free language is a bit different. We're going to relax that restriction about needing a finite amount of memory. But we have a very limited structure of infinite memory that we can use. So we need additional memory in our control unit for the state machine. That's the basic conclusion we're going to draw from this, is that now a part of our state machine needs to be memory. And that's what we are going to add to this process. We're going to be taking along with us, visiting every state, an infinite stack. So is there a limit to the amount of memory needed to be able to accept or reject a context-free language? The answer is no. We don't. As an example of this, take a simple language that we proved was not regular. Just as a refresher, why wasn't A to the N, B to the N regular? At an intuitive level. Why is this language not regular?
You're always gonna have the same number of A's as B's, so the only way you can really put it in the terminal or non-terminal is gonna be in the middle of those two.
Yeah, once we have to count the number of A's to be able to match each B to an associated A that we'd seen already. When we make that transition, we have to know how many A's we saw. And no finite DFA can do that. We could be able to say A to the N, B to the N, where N is less than or equal to 10, and then we could make a 20-state DFA that says read A's up to 10 of them, and whenever you see your first B, transition and work your way backwards to a final state based on how many states you saw. So you kind of make a weird C-like shape or reverse C-like shape, depending on how many you saw. But if you can have up to an infinite number of A's and B's, then that C can be arbitrarily long as you go and need to be able to match that. So no finite size DFA is going to be able to recognize this language. You would need an infinite number of states. So we know the language isn't regular. Maximum number of A's that can come before the B's, no. So in the worst case, how much memory do we need to be able to accept or reject all strings in this language? The answer is infinite. So we're going to use this as a motivation to say, how could we build some kind of state machine to accept a language like this? What do we need to add? It is an infinite stack because that makes sense, right? You push the A's onto a stack as you go and read them. And then as you read B's, you're going to start popping A's off the stack. And if the stack ends up empty, meaning that there were no B's left, and it followed the associated form, I saw all of the A's before I saw B's, then we could accept. And if we had such an infinite stack that could hold an infinite number of A's and B's, then we would be able to accept this language or reject this language for an arbitrary number of A's and B's. So it's exactly like an NFA with a pretty significant number of changes, but we're going to start our understanding of this at a baseline for as an NFA. So what changes need to be made to an NFA to make a PDA? And again, PDA stands for push down automata, not public displays of automata, not public displays of affection. Any ways that you would have seen this before. I really like public displays of automata though. It's such a great. Anyway, I'm done with that. I'm done making that joke now. So we do need some technical language to define the stack alphabet and the stack start symbol. So we're gonna, again, look at this from a definitional perspective and then come back on everything that this means. So here is the definitional perspective. So it looks kind of like an NFA, but there are a couple things that are different. The big differences are here in bold from the NFA. We're going to have a set of symbols that we're going to call the stack alphabet. And we're going to have the stack start symbol tell us what is on the stack to denote that it is empty. Because programmatically, we can just call an isEmpty method that returns a Boolean yes or no. In terms of how we're going to be looking at this theoretically, we can't easily determine isEmpty. So we're going to put a particular symbol on the bottom of the stack that denotes that it is empty. The very first thing we do is push that symbol. And if at the end of all of this, the stack is empty, we can call pop on that and we should expect to get the stack start symbol. So visually, this looks very similar to the NFA, except now we have this stack that the control unit can use. I like to think of it as it actually moves around the states with it. You're moving from state to state, but it's the stack that's moving there. And based on the transition that we are taking, not only can we read input characters in the string, we can also manipulate the stack. So now we have 2 points of control as we construct these. We construct the transitions of the characters in the input that we read as we move from state to state. We also make associated changes to the stack as we make those transitions. So the transition function now includes this stack alphabet. When we make a transition, we are moving from one state to another state and also pushing or popping from the stack. We'll define exactly how to write that here momentarily, but that's the intuitive idea. 2 points of control, reading characters from the input string, and manipulating the stack. Questions on anything from this slide? All right. The domain and range of the transition function are going to change. We've already talked about this, but rather than just consuming an input character or not doing this on a lambda transition, this is why we're using an NFA as the baseline for this, because there will be a limited form of lambda transition that is okay. We also need to make an associated change to the stack. It can be a push, a pop, or nothing, but we're going to call it no op. Just means that we're doing nothing to the stack. If the stack is empty, we cannot make a move. We have to reject, basically, if the stack is empty. Note that the stack is not empty if the bottom of stack character is still on it. Once you remove the bottom of stack character, you're at a point where you can either accept or reject. We also need to state that the range of the transition function is finite. This is necessary. Otherwise, you can make an infinitely large PDA. In order for the PDA to be finitely sized, the transition function must be finite. And even though we're carrying an infinite amount of memory, the number of states and transitions in this system must be finite. This tells us an additional thing, that the subset of possible strings that we're going to push to or pop from the stack must also be finite. So we are starting looking at this from an NPDA perspective, meaning a non-deterministic push-down automata. Why? Because they're significantly easier than DPDAs. We'll talk about this as we get there, but we started with a DFA because it had the easiest to understand and simplest rule set. We came up with an NFA from the DFA, coming up with what the changes to that would be. So we're going to be tackling this from the opposite direction. Here is an example of what a transition on an NPDA looks like. Does anyone have any idea what this means? The text is here, but can someone summarize this text into what does this mean? It's a very mathy notation. So the from arrow in an NPDA is no longer just an outgoing arrow from a state with an input symbol. We also now need to identify the top of the stack character. And we're going to assume that that top of stack character gets popped already. If we want to do a no-op, this pop and the associated push at the destination will be the same character. So we're assuming we are leaving state Q1 via an out edge. The character in the string that we are consuming as we do this is an A. So the character that we are currently on in the input string must be an A. And when we pop the stack, that character at the top of the stack needs to be a B. We cannot traverse this edge if all three of those things are not true. We're in state Q1, the next character in the input string is an A, and the top of stack character is a B. So we have a triple here, a tuple of size 3. And that's what those three elements mean. So we're going to see the delta, outgoing state, input character, or string character red, top of stack character. That tells us everything that needs to be true to traverse the edge. What we see on the other side is now not just where this leads, but because it's an NPDA, there may be multiple places that we can go on a particular, this is the same thing as, having an A that goes to one state and an A that goes to another state in an NFA. But now we're going to represent this again as a set, the set being every possible destination of such an out edge. So this out edge can either go to state Q2, and when it gets there, it's going to push CD onto the stack. Or it can get to Q3 and push nothing, which means that it popped the B.
So is A put on the stack or no, it's just what was read?
No, that's read from the string. Yeah, only the last element of the triple has to do with the stack. So every destination is a tuple, and the out edge is a triple. Triple to some number of tuples, comma separated. Much more complicated than how we represented DFAs and NFAs. We're going to find that NPDAs also look a bit different in that they're really hard to draw. DFAs and NFAs were great for visualizing these problems, and we will find that NPDAs often are just a giant mess. Very few states, and each of those states have a ridiculous number of edges. So let's give you an example. Here is a definition, and again, I'm not drawing this out, but I want people to attempt to do so. So just like in an NFA, transitions are not always specified. If there is no transition, we assume that we just automatically reject. Just like with an NFA. So what does this mean? Is there a way that we could draw this system? We know there are 4 states, Q0, Q1, Q2, and Q3. There are transitions associated with each. Note that we have a different string alphabet than we have a stack alphabet. In the string, we are reading A's and B's, but in the stack, we are pushing and popping 0s and 1s. This is mostly for readability at this point. You can have the same language. C and A, push an A, like we were doing A to the N, B to the N, it might make sense for the stacked characters to be the same characters that you would see in the string. But as you're just learning to read this notation, it's good to separate what is something that would appear in the string versus something that would appear on the stack. So I'm using a different alphabet here for that reason. But what does this actually look like? And see if you can find the meaning behind it. What is this state machine actually doing? remember that this symbol that gets popped here is popped regardless. So if you see something like 1 with 1, 1, this is a push of a single one. We pop a 1, push it back on and push another 1.
So the one is not 11, it's just 2 ones.
Correct.
It's. We're pushing both ones on the stack.
Yeah, pushing 2 1s, the one we popped and another one. And also the top of stack character here is the 1. So we pop a 0. We're gonna push the 0 and then the 1. So the new top of stack character is a 1. That's the other, I guess, point of confusion you might have. We think we have it written out. Looks like people might be getting to that point.
So
Yeah,
so it's Q0, then it's the input, then it's, what is the last one? Is it push or is it pop?
it's being popped from the stack.
The last one is a push.
Yeah, the last one in the second element of these tuples are what's being pushed to the stack after this was popped. In the order of this, the right side on the bottom of the stack, the left side on the top of the stack.
So what's the difference? You have two separate lines going from one state to the same state.
Yes, yes, as long as they're either doing different things to the stack. Or reading different characters from the input. So just like in NFA, as long as the entire thing is not the same, then it's distinct.
So how do you pop something that's not on this, or if the stack is empty? Like
If the stack is empty, you reject.
so Q0, lambda 0 to Q3 lambda, that's not doing anything, is it?
It's popping a 0 off the stack.
How can you do that from the beginning if there's nothing to start with? Or is that what
The
this?
bottom of stack character is a 0. So as you move to that initial state, a 0 should be on the stack. Okay. The 0 is only there, basically. If you've done this correctly, then the only 0 is at the bottom of the stack that tells you that the stack is empty. A 1 is going to tell us something else. There's only ever 1 0, and it's always at the bottom of the stack.
And so on the 10, or on the 10, I guess, which one is on the top of the stack at the end of it? Is it the 0 or the 1?
Yeah, 0 is on the bottom because 0 is going to be that bottom of stack character. We never add extra zeros. We're only ever replacing the existing bottom of stack 0. This basically is going to say, if we're in the case that there's nothing on the stack except for that bottom of stack character, we have to pop a character. We're going to push it back on and an additional 1 on top of it. So if we wanted to draw some conclusions from this, looking at all of this in general, what are some things that are happening? So when we see an A, what happens?
When you see an A, you pop a 0 off the stack. Then if you go to Q1, you put a 0 back on, followed by a 1. Then if
You're looking at this kind of on a transition by transition basis. Try to abstract from this and say, wherever we see an A, what do those rules have in common?
you pop a 0 off this,
There might not be a 0 on top of the stack. Yeah, whatever is on the stack, we're just gonna push a 1 on top of it. That's true for each of these. If a 0 is on the stack, put a 1 on top of it. If a 1 is on top of the stack, put another 1 on top of it. Yeah, exactly. So I like to, you see this as just a bunch of transitions, but the skill here is being able to take this, abstract from it and say, what is this actually doing? What is common between these rules? That will help you to also go the other way. When I say, break down this problem and write an NPDA for it, then you can think of what general rules do I need to represent? What are the different components of those rules? What are the possible states of that? If a 0 is on the stack, if a 1 is on the stack, I need to write 2 different rules for that. If I'm going to put a 1 on top of the stack when I read an A. Now, there's not just one rule for that. There's a rule for that for potentially every possible stack character that could be on top of the stack. This is why this is significantly more complicated than DFAs and NFAs. So what happens when a B is read? So I will reveal this now. When an A is read, we add a 1 to the stack. What happens when a B is read?
Off the top of the stack.
Yeah, we're gonna take whatever is on top of the stack and we're gonna get rid of it. But is there anything that says read a B and there being a 0 on top of the stack? No. What does that mean?
It's a useless production.
It's we don't need to specify every transition. If we ever are in that case, we reject. Just like with an NFA, if there's no transition with that rule, there's nothing to do. There's no way that we can get to an accepting state, so we're just going to reject. So we only need to write the rules that could lead us to an accepting state. But yes, we are going to pop a 1 from the stack whenever a B is read. If a 1 is not on top of the stack, something has gone wrong. There's no such string in the language. Note, we have transitions from Q1 to Q2 after the last A is read. So we're going to be reading a bunch of A's, adding a bunch of 1s. This gets us into Q1. Note that there's no way to loop back to Q0. So once we move to Q1, we're reading a bunch of A's. Once we read our first B, there's no way to get back to Q1. Q0 exists to put that top of stack, the bottom of stack character. Q0 is to say, all right, if there's nothing in the string, move directly to the accepting state. This says that we accept the empty string. Since there's no way to get back to Q0, this rule is only valid in that one time to accept the empty string. Once we read our first A, we transition to Q1. From Q1, all we can do is read a bunch of A's, looping back to Q1, or read our first B, which transitions to Q2. No way to get back to Q1. Once we finish reading A's, we can't read any more A's. If we ever see another A again, we reject.
So. Kind of. Going forward with it, is it popping off the bottom or the top of the stack?
Top. We have no way to access the bottom of the stack.
Okay, and it's a push down. So on Q2, when to 0, you read nothing. Is that, how does that pop a 0 off the top when there's no zeros that can be there?
It's the bottom of stack character. The only time this will be valid is if we've removed all of the 1s. If all of the 1s that we put on the stack when we're reading A's are gone,
So Q2
only
is,
then can we transition to a final state.
okay, so it's reading a B, popping a 1, and then pushing a lambda on the stack until there's only 1.
Well, the
there's only
lambda
first-
is nothing. Remember, this is kind of a no op. So you're popping a 1 and pushing nothing
Yes, you're just removing one, and then
Yeah.
you do that until the 0 comes back up. Then you go-
until the 0 is there. And then for nothing, we transition to the final state. But now note, from this final state, there's nothing that says read an A or read a B. So just because we've reached a final state does not mean that we accept. We have to be at the end of the input string.
So lambda in the first part is basically saying we're at the end of the.
A lambda here basically
Yeah.
says you don't have to read a character to be able to do so. You can make a lambda transition in the middle of a string, just like with an NFA. But this is designed in such a way that the only time you would be in these cases is if you're at the end of the string, or if you've read A to the N, B to the N, and there would be more B's after that. You could make a lambda transition to the final state, but then you wouldn't be at the end of the input string. And you'd have to read a B. There's nothing you can do from that accepting state, so you would immediately reject, even though you're at a final state. You can't accept until you're at a final state, you're at the end of the input, the stack is empty. Or you just have the bottom of the stack character, but in this case, we're getting rid of it, and you end up with an empty stack. So those are the 3 conditions to accept. You're in a final state, you're at the end of the input string, and the stack is empty. If those 3 conditions aren't met, you reject. So we end up with a diagram that looks something like this. And you will find that we need 3 things now on each of these transitions that represent these things. So we are from Q0, reading an A, popping a 0, pushing a 1, 0. So the transitions tell us 3 things, in addition to the out edge and the in edge. So if you're reading this, this is the state, Q0, A, and 0 comes from here. And then Q1, 1, 0 is there. Q1, A1, Q1, A1, back to Q1, 1, 1, back to Q1, 1, 1. So that's how we're going to read that. And this recognizes the language A to the N, B to the N. That was part of our motivation to say we could not come up with a finite state machine with a finite number of states to represent the language. But as soon as we allow an infinite memory stack, we can come up with a 4-state NPDA that recognizes it, as long as we have access to that infinite stack. So change the rules a little bit, and we have some way to represent it. Of course, now we're starting to get into the realm of theoretical computer science, because who has ever seen an infinite stack before? Is there any hardware out there on this planet that can allocate memory for an infinite stack? No. So we're going to transition from this. Once we're done talking about all the ways to talk about context-free languages, we're going to start talking about theoretically what is possible versus today what is possible. Theoretically, there is no limit to the amount of memory that we could allocate. There's only the physics of how many transistors can we put on a CPU chip? How much memory can we shove into a physical system? Some server that can be allocated for something. Those are the limitations on what we can actually do. But it's worth studying if we had infinitely powerful CPUs and infinite RAM, what could we do? What could we calculate? What kinds of problems could we solve? So we'll get to that in a bit. But so this is kind of a theoretical state machine to represent a language that you get an idea of what we could do with a finite amount of memory, but a scalable amount of memory. So that's kind of the application of what we're doing. Okay, now there's one other form of notation. This is a very notation-heavy class that we need to figure out. So we introduced this concept of writing out the transitions like this, taking these transition ideas, writing them in diagrams. Any questions on that before we introduce one other notation type? All right, we need to figure out how to do instantaneous descriptions. Because with an NFA or a DFA, the only thing that was changing was the location in the string. So we had some string and we kind of point to, this is the current character that we were reading. But now we need to point to that, and we need to point to the place on the stack where we are, what characters are on the stack. So we need some way, if we're going to be parsing through a string, to say, what is the state of this right now? What are the contents of the stack? What is the current string? What is the character we are on? So transition graphs are really useful for a DFA or an NFA. You can tell at a snapshot where you are, but less useful for PDAs because we need to keep track of all of this. So we need a new notation to talk about this. So the notation is going to be something like this. We're going to have a triple QWU that tells us the state of the control unit. So are we in state Q0? Are we in state Q2? Are we in state Q8? That's going to tell us Q. W is just the unread portion of the string. So what is left to be consumed in the input string? And finally, U is the entirety of the stack contents. This gives us an at-a-glance look of where we are in this system. If we use the turnstile symbol here, this will tell us that we are moving from one instantaneous description to another. In math notation, you would say, it is provable that we can get from this state to this state. We can also use this to show step by step how we accept or reject a particular string by going through this NPDA that we've constructed. In general, we're gonna start using the letter Z to represent the bottom of stack symbol because it's just not used for many other things. So Z in general is that bottom of stack character. You'll want to start using that as the, basically, as we transition into Q0, that start state, we're going to be pushing Z to the bottom of the stack. That's inherent in, we're starting at Q0. That means that Z is on the bottom of the stack. Which is also now the top of the stack, I guess. Questions on any of this notation? We'll get an example with it here momentarily, but I just want to make sure that the concept is clear. All right, write an NPDA for this language. So a string W in AB star such that the number of A's and of W is equal to the number of B's of W. So now we're not specifying that all of the A's have to come before all of the B's. We just care that by the time we reach the end of the input, that we've seen the same number of A's as we have B's. Before you get too deep into this, think about algorithmically, how would you solve this with a stack? Imagine instantiating a stack in some programming language and then saying, all right, we're gonna read some character, pushing and popping characters to the stack. How would you solve that? What would you push to the stack? And what would the stack's contents represent at that particular point in time? Like, let's say, when I see an A, I wanna push an A. When I see a B, I want to push a B. This is not a complete solution. But in that case, what would the stack's contents represent? The number of A's and B's that I've seen so far in the string. Again, don't run with that because it's wrong. But think about whatever algorithm you would use for what's on the stack. Think about what that would represent about what you'd seen so far in the string. And that will tell you how to proceed. Rather than immediately starting to draw an NPDA, spend some time designing it in your head. Really have an answer for what does that stack represent?
You just want just like a list of like stuff in the parentheses, like the Q to W, you just want steps, so it's.
No, this should be actually drawing it out. It's either an NPDA or defining the transitions in a list of transitions. Whatever you think would be most useful. I'm gonna argue that you may want to actually write out the transitions because the actual drawn NPDA for this is gonna start to look like how some of these NPDAs look. That is, the visual doesn't really help much. And I will draw it out as a visual just to show you what that looks like. But it's kind of gross. In fact, I will give you this hint as well. This has 3 states. And way more than 3 transitions. Does anyone come up with an idea for what you would use for your stack? What symbols are you using and what do those symbols represent? I'm gonna draw you a diagram that might help. Does what I'm trying to communicate here make sense? This is as we read W, whether we've seen more A's than B's or more B's than A's at that point in the string. If at the very end of W, we've seen the same number of A's and B's, we can accept. But we need to keep track of not the cumulative number of A's and B's that we've seen, but just as we read each character, how many more A's than B's have we seen? Or how many more B's than A's have we seen? I would argue that we can emulate that with a stack. How do we do it? This would be something like we see A, B, 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 A, B, A, B, B, A, B, B, A. Doesn't work, does it? If this is two B's, then we need two A's somewhere. This will be A. Why not? It's not quite right visually, but now it at least has the same number of A's and B's in it. So when we go up, we read an A. When we go down, we read a B. Whenever we cross the line here, we're moving from having seen more A's than B's to seeing more B's than A's. We're having seen more B's than A's to more A's than B's. And the distance from this line tells you how many more A's than B's you've seen, or how many more B's than A's you've seen. If we end back on the line, we accept. If we end somewhere off the line, we reject. That would just be another way to visualize this. Fortunately, out of time for the day, but my challenge for you between today and tomorrow is try to finish this off. See if you can come up with some solution to this, and at the start of class tomorrow, we'll go over said solution. I'll also get up your next homework assignment. What I don't know is if it will be due next Wednesday or the following Wednesday. We have an exam next Friday. So you will expect a study guide. You can expect a study guide by tomorrow, but I'm gonna try to get it out to you today. And I will reveal the homework. The question is just, is it due in 1 week or 2 weeks? Because we haven't really touched on too much new material yet. I don't want people focusing on a ton of homework over studying for an exam. So we will see if it makes sense. All right, see you all tomorrow. I have office hours starting now if you have any questions.